we say that you have achieved the eucentric height of the sample. Eucentric height of the sample is the one at which the sample should be as per description of the machine. If the sample is not there, then whatever you do will not be reliable. Because there is a perfect specific position for the sample to be. So if at that position I tilt the sample and it is not shifting but tilting at the same position, then we say the machine is eucentric height corrected. If you take the image or diffraction pattern when the eucentric height has not been achieved, then you can't say that what I am measuring is correct. There will be variation in your measurements because your sample is shifting and it is not at the eucentric height. Look into this. Likewise, the position of the specimen relative to the beam is of critical importance, and to adjust the height Z, as I told you, this in the middle, this is the 3 millimeter disc of the sample, and you can move it like this, this, and this. And what they say, to adjust the height or Z position of the specimen, it is physically rocked back and forth until an object in the center no longer moves. You select a feature in your sample, you select a feature in your sample. This is the room, and I selected those set of plugs there. And when I move the room like this, and that are not changing the position, that specific feature, because I need a distinguishable feature to start from, to focus upon. I can't look at every point in the sample. But if I am tilting the goniometer and the sample is tilting, and that feature is tilting as well, but not changing the position, then I say it is aligned. These are the shifts and translators of different things. Specimen holder, as I have shown you, this is the tip of the specimen holder on the top, right? And in the tip, you have a small 3 millimeter space for the sample where you put the sample. The sample, which is electron transparent, is usually very, very thin. And when you hold it with tweezer, there is a lot of chance that you break the sample. When you hold the sample with tweezer, there is probability, a lot of more probability that you will break the sample. If the sample is transparent and you drop it on the floor, then it is very difficult to find that sample again. When it's 3 millimeter is the diameter of the sample and the thickness in nanometers and angstrom, so it is very difficult to find such a sample. So the electron microscopist must be very, very careful. Secondly, when you put the sample here and you are putting it with tweezer, there is a chance that you may damage the sample. If you don't break the sample with a lot of movements, you can break the thin area of the sample. For example, a blow can break that, right? Air blow can break that. So, when the sample was very, very thin and very, very brittle, and I am not sure that whether if I hold it with the tweezer, it will be safe or not, then there used to be a vacuum tweezer. Vacuum tweezer is pulling back the air, and there is a spot there. And when you open it, and it holds the side of the sample, then you lock it. So the sample comes with the vacuum tweezer. And you put the sample in the proper place, and when you release that knob, that hole, then the sample is dropped there. So that is the safe way. But this never means all the people are doing microscopy, and many of them are not breaking their sample. So, but extra care is always needed. So, specimen airlock evacuated by a separate line from the mechanical pump. This avoids the need to ventilate the entire column, as I told you, in order to insert a specimen. These are the shifters, the tilts, that when you move this, you are moving the sample inside the machine. Because the sample is 3 millimeter diameter and the thin area may be less than 1 millimeter, right? But when you look into it at a magnification of 10,000, then it is not 1 millimeter but 10,000 millimeter. And if you look into it at magnification of 1 million times, then 1 millimeter is 10 million and 1 million millimeters. So it is a big world inside that sample. And you will get tired by moving the sample, and when you lose an area, it is difficult to find it again usually. It is so big world inside that 1 millimeter thin area. So people are moving the sample around on the screen and bringing different regions of the sample by using these knobs. Tilt stages enable tilting of the specimen for stereoscopic viewing, eccentric tilting, rotation, and tilt with image shift around a common axis. And you see here, there it is not proper, and it is proper that it doesn't change the position. Here the position is changed with tilting, right? There is another feature, because with the time people are learning, and the sample position in the microscope, the sample space in the microscope was a very difficult situation. A major problem with TM lens design is the fact that there is very little space between the pole pieces of the objective lens to accommodate the specimen and objective aperture. This also puts severe constraints on how far the specimen can be tilted within the machine. Because if the objective lens is here, and then the aperture is somewhere here, and you are moving the sample, and you can't move it. Right? If I shift it like this, it touches this area, and I can't break the aperture or the lenses. Although they are fields, but the aperture is aperture. So you can't move things freely there. And for this purpose, they came to the double objective lenses. A clever solution to this problem came in the invention of the double objective or twin lens. In this lens design, the specimen actually lies between two separate lens fields, allowing for tilt angle as large as 60 degrees from the perpendicular to the optical axis. You are moving the optical axis like this, and you are here, moment are here. So they are perpendicular to the optic axis. Now, look at this. Focus wobbler shifts the image back and forth, and when the movement is stable, the image is focused. You see their edges, so it is not focused. Then if you further take it, look at these lines, and you are basically moving these lines, that when these lines reach the perfect place and you see the sharp edges with no lines like that, and you see the images in focus. So An inexperienced person can easily deceive himself or herself if he or she doesn't know the actual focus of the crystal. You can make a rectangle from a square by misaligning the microscope. So always when people get some results from the highly sophisticated techniques, then they straight away go to literature, that whether other people are reporting the same thing or I am reporting something unusual. If you are reporting something unusual, then go back to your machine and refocus it, relook into it. And if it is again coming, then show it to some experienced person. That is it in fact a different result than the one reported, or I am doing some mistake. So if you are doing some mistake, then you will be corrected by the expert. And if it is really a new result, then it is a novel result and it is publishable. Right? But several times people check before reporting any new result. And here is the holistic picture, that this is the high voltage source of electron guns, anode, condenser aperture, specimen airlock objective, condenser lens, projector lenses, turbo pump to evacuate the column of the machine, rotary pump, viewing scope, binocular, viewpoint when the viewer is looking into it, and this is the fluorescent screen which gives you the image or the diffraction pattern. But when you are taking the diffraction pattern, you project the big focal plane onto the viewing screen. And when you are taking the image, then you are projecting the image onto the viewing screen. And you can easily move up the screen. It automatically moves up in the modern machines, and the image or diffraction piles upon the negative film and you take the image. But in the modern machines, we have now digital imaging, and the image can be recorded by the computer. In the old days, people didn't like computer generated things, but the camera which is used in transmission electron microscope is a very highly sophisticated camera. So it is not harming any information or losing any information when you are taking images on that. And important thing is how much resolution the camera has. So if you are interested in angstrom level, the dimensions of angstrom features, and the camera cannot resolve an nanometer scale thing, then obviously the information is lost. And that is why very high resolution cameras are used for recording the electron microscope images and diffraction patterns. Thank you. That was for today. Any question, please?
This is the binocular of electron microscope. Is that a reflected electron beam?
No. This is just magnifying the screen for us. When we look into it, the whatever is present on the screen appears 10 times larger in the binoculars.